best value in the world, it works. So we don't plug in any values for x, we just use our formulas. So we rewrite this side, and then we rewrite this side. All right. The people who know what formulas on their formula sheet do well in proofs. The people who do not and go searching do not do well in proofs. Okay? So 1 minus sine squared x, what could I replace that with? Ooh, what? Cos squared. So this equals cos squared x. So do you see how I wrote 1 minus sine squared because that was the first thing that was given to me? You need to do that as well. You can't just write cos squared here, which is what I get a lot of people doing. Because the proof is, I started to look at the top left and I work my way down, that would be the proof on the left side. Okay, that looks as simple as I can get it. The single one, sine, cos, cotan, if they're double, you can, or squared, you can use all the squared ones. If they're just singles, you can use only the formulas at the top. So sine and cos is usually what you want to keep them as. But I can change the cotan to something else. So this is going to be sine x over 1 times cos x over 1. What's cotan? What is cotan x? Cos x over sine x. Now some people tell me, oh, it's tan, 1 over tan. Cool, not helpful. All right. We're not saying restrictions right now. We're literally just doing, throw in that. We're literally just doing what we tend to cancel. So, in this case, because they're all monomials, I can cross the sine x to the sine x. That should make you happy, because what do we ultimately need to get that side to be the same as? Cos squared. What's cos x times cos x? So a lot of people will write this and then go ls equals rs. Okay, inside scoop. My grandma Hamill, lovely lady, love her pieces. She's going to be 90. She has to be able to look at this and say, those two match. Currently, although she was a teacher in her day, she taught grade 1 and 2, she would not know that this equals this. You'd be like, well, it's obvious. Obvious? No, it's not obvious to her. So unless she knows that the images are the same, you ain't done. Okay? So what are we going to have to do to this side? Rewrite it as cos squared x. Now would my grandma Hamill agree that those look like the same thing? Yeah. Yes. And she would be okay with it. All right. All right. Don't die on me now. Okay. Shh. You guys try too. Go quickly. Math. So if you don't know your rational rules, you will cross off things you should not cross off. That goes poorly. That's number 1. Number 2, the other place where errors happen is you actually don't know how to do fraction rules. Because there has to be fractions, right? That's where the things happen. So 1 minus cos squared I can replace with sine squared x. And then I know that this side somehow has to turn into a sine and a sine, right? So let's switch these two sines and cos where possible. So tan x is sine x over cos x times cos x over 1. And then I get a big fraction as 1 over sine x. Okay. There are some people that are good with visualizing dividing by fractions, like multiplying by it, and then they can do it all in their heads. Then there are a lot more people who can't. Okay? So don't. This cos x and this cos x can cancel, and then I'm left with sine x over 1 divided by 1 over sine x. So if the denominator cancels off the denominator, I stack them, it's easy, right? But when they don't just divide off, it's a lot easier to actually just write them side by side instead of stacked. And then instead of dividing, you end up inverting and multiplying what you're dividing by, so the reciprocal. So you actually end up multiplying by sine x over 1. And then a lot more people can see that that's sine squared x than visualizing the flip and the keep. So write it down, Campbell.
I did.
You did? You already did? Okay. Ls equals rs. Because Grandma Hamill would now say those are the same. Okay? Let's look at the third one. So the third one says, prove that tan x equals 1 minus cos 2x sine 2x. Yes? Okay. Let's write this out. LS, RS, tan x, 1 minus cos 2x over sine 2x. You see how in the very first step, I literally just rewrite it into the table. I don't change anything. Sine 2x, I can change to 2 sine x cos x. There's only one formula for that. They're all multiplied together, so I can put them in their own separate brackets. And tan x we know is the same as sine x over cos x, correct? Now what you can remember or realize is that both sides are trying to become the same thing, yes? This denominator on the left-hand side has a cos x, so I want that to stay, yeah? And that 2 and that sine need to get out of my life. We agree? Are there any cos 2x formulas that if I rearrange it will give me 1 minus cos 2x? Are there any formulas over here that if I rearrange it will give me 1 minus cos 2x? This one, yeah, the cos 2x equals 1 minus 2. I'll do it over here. So cos 2x equals 1 minus 2 sine squared x, correct? So how can I rearrange that formula to get 1 minus cos 2x? Move this over here by subtracting it, correct? And move this over here by adding, right? So I'm going to add the 2 sine squared x over to this side. The 1 stays here, and then I'm going to move the cos 2x over here by subtracting it because it's addition rate. You see how I just arranged that formula? That's all I did? Yeah? So now I can take that 1 minus cos 2x off the board, throw it away, and replace it with what? 2 sine squared x. Which makes me happy, because what did I need to cancel in the denominator? The sine and the 2. So the 2 can go away, because it's a monomial and a monomial. And this sine can cross off one of those, because they're monomials. Remember, sine squared x is the same as writing sine x and sine x, right? So I can either cross the squared off like that, or I could just rewrite it twice, and then cross one off for 1, right? Like it would get me the same thing. Yeah? And so then I would end up with sine x over cos x. And would Grandma Hamlin all those look the same? Yeah. So we say LS equals RS. Now what some people do is they'll just leave it at tan x, and they'll turn this right side into tan x. Would they then match? Yeah, that's totally fine. So what you have to do is, sometimes you will do it a different way than I do it. And it works. Sometimes you make it work, and you get left side equals right side, but you do a whole lot of illegal math. And so then it doesn't actually work, right? You just like, I can cross this off. I'm like, no, you can't. I can cross this off. I'm like, nope. And I can't cross. I'm like, no. So if you don't do it the way that I do it, does it mean it's wrong right away? No. Call me over and ask me, did I illegally math, or is this okay? And a lot of the time it's okay. Okay, you guys try 4. Go. So we have LS, RS. Okay. And then we have sine 2x over cos 2x plus 1. Okay. Sine 2x is 2 sine x, guys. Stop talking. 2 sine x cos x. Don't give me that look. You know it was you. 2 sine x cos x. We're recording. Quiet down, bus. Throw her under. Okay. Cos 2x plus 1. Cos 2x plus 1, what can we replace it with? 2 cos squared? Yeah. Okay, this cancels this cancels this, and I'm left with tan x. Okay, it gets harder. Flip over. Yeah. All right. So, listen to me. Pencils down. All brain matter. Given up here. No talking. You will miss a very important piece of information, which will rook you for half of your proofs. Okay? In grade 10, you were taught if you have x squared minus 4 and I asked you to factor, what type of factoring is that? Difference of squares. So you would take the square root of the first one and you'd get an x in the front of each bracket. The square root of 4, you get a 2 at the back, and then opposite signs. Okay, did you know that a difference of squares is just conjugates? That's all the difference of squares is. Because when you multiply by a conjugate, you get your middle term to cancel off. That is the goal of multiplying by a conjugate. So when you multiply by a conjugate with radicals, it gets rid of the middle terms where the radical still exists, yes? But same thing with difference of squares. Because you're going to get a minus 2x and a plus 2x. That middle term's going to go away, and we're going to be left with negative 4. Yeah? Okay. What if I give you this? What is that? That is not nothing. All right. This is a what? Difference of squares. Same thing. I take the square root of the front bracket. What do I get? Sine x. The front of each. What do I get at the back of each? A 1, a plus 1, and a minus 1. Now, people do not spot difference of squares when one of the numbers is a 1. If it's a 4 or a 9 or a 16 or a 25, people often spot those as perfect squares, but ones they don't. Okay, are we still watching? So, I can go from a difference of squares to a conjugate, correct? Now, think about this. 1 minus sine squared x. What is that? Is 1 a perfect square? Is sine squared a perfect square? Is that a difference sign? Yes. So this is also a difference of squares. Square root of 1 is 1. It goes to the front of each bracket. Square root. Square root of sine squared is sine x. It goes at the back. And then we get plus or minus. Yes? Okay, are you listening? Hands to yourselves. All right, it's like kindergarten children, except worse, because you're giants. All right, giant kindergarten children. Okay. So 1 minus sine squared x could be written as a difference of squares. Yes? What else could 1 minus sine squared x be written as? Cos squared x, can it not?
Yes.
So, if I have two conjugates with like a 1 or a negative 1 involved, right? They can be rewritten as like 1 minus sine squared, which can be rewritten as cos squared. So those are all interchangeable, correct? So if we go back to this question, and I write it out, I have LSRS. I have 1 minus cos x over sine x. And I have sine x over 1 plus cos x. If you do not pay attention, you will be lost and never get this. So this is the time that you're going to figure out how to pay attention. This is the moment. I can't switch them into sines and coses. They already are. Right? There's nothing more I can do. I can't do the squared equations. There's no squares on here. We agree? Okay. I do, however, see that this is a binomial here, so I'm going to put brackets around it. If there was, and this is a binomial, if there was a cos x on the top of this right side, I wouldn't be able to cross this cos x off with that, Because the sine x is a monomial and this is a binomial. You can only cross binomials off for binomials and monomials for monomials, okay? I do know that I want a sine x in the bottom. Do you see that? I want a sine x on the bottom. I do not have that currently, do I? If I have a 1 plus cos or a 1 minus cos or a 1 plus sine or a 1 minus sine, I know I can multiply by the conjugate and get like a 1 minus sine squared or 1 plus cos squared, and then I can use my Pythagorean theorem identity. So whenever you're stuck, if you're given a 1 plus cos or a 1 minus cos, pick one of the sides, not both. You don't work on both, or you're just getting further away from the same answer. I'm going to take this one, and I'm going to multiply it by 1 minus cos x. And I'm going to multiply the top by 1 minus cos x. Now, you are going to have to watch yourselves. You will distribute the conjugates. Because when you distribute the conjugates, you get a difference of squares. Do you not? That's the point I just showed you. Difference of squares turns into conjugates. Conjugates works into difference of squares. Yes? They're the same? We discussed this. So, if I have this, I'm going to get 1. And then I get a minus cos x plus cos x, so those cancel. And then I get a minus, that's supposed to be the denominator, sorry. I get a 1 minus cos squared x on the bottom. Okay? This is where you're going to have to stop yourself. Okay. So, leave yourself a little note at the top of this paper. Right, Luke? Leave yourself a note at the top of this paper that says, distribute conjugates. Do not distribute the terms that are not conjugates. C-O-N-J-U-G-A-T-E-S. Conjugates. Con. C-O-N. J-U. Gates. G-A-T-E-S. So, we are going to, guys, quiet. We're going to multiply. Same turn, opposite sign.
Wait, can you repeat the sentence?
We are going to multiply the conjugates together. But we are not going to multiply the ones that are not conjugates together. So you multiply the conjugates together, and then leave the ones that are not conjugates separate. Now, why would we do that? Remember, I told you, great that we get memorization tactics, but we have to understand why we do it so we don't screw up. So the reason why is this. If you look now, look at this numerator. Oh, no, you didn't, girl. Oh, no, you didn't. All right, so if we look at this numerator, what is currently in this numerator? 1 minus cos x, yes?
Yes.
What is in this numerator? 1 minus cos x. So these are going to be the same, but I need to get this to get out of my life. Do we all see that? So if I take that sine x and distribute it in, I'm going to get sine x minus sine cos x. Am I ever going to see that I need to get that sine to go away? No. So that's why I just said to you, you distribute the conjugates, and the one that are not conjugates you leave separate because you want half of it to go away. I want to keep this. I want the sine x to go away. In order to get a sine x to go away, I need a sine x in the denominator. Is there any way I can get 1 minus cos squared x to be sine x of some sort? What is 1 minus cos squared x the same as? Sine squared x from the Pythagorean identity. That's why you multiply by conjugates. So we're going to get sine squared x here. And then the top we have sine x, 1 minus cos x. And we get 1 minus cos x over sine x. And then they match. LS equals RS. Okay. We're going to look at 6. So we have LS, RS. Here we have 1 over 1 plus sine x. The only thing I could do to this side is possibly multiply by the conjugate of 1 minus sine x. This side is more advanced. more complicated. 97% of the time, if you are stuck, it's because you're not spotting a difference of squares, multiplying by conjugate, same thing, or you don't spot a GCF. So we're going to look at the right-hand side. Is there anything I can do to that numerator? Take out a secant x. Because this term has a secant and so does that one. So I GCF out a secant. Remember, when you take out a GCF out of two terms, you still have two terms left. Because if I distributed it back in, I should get what I previously had. Yes? So logic people will tell me, oh, secant, and then it's just minus sine x. No. Secant divided by secant is 1 minus sine x secant x, take out a secant x, is sine x. Now I know I'm right if I go secant times 1 gives me secant x, secant times negative sine x gives me that back, right? Whenever you take out a GCF, you should be able to check if you're right, because you should get back what you had. If you don't get back what you had, you messed up. And then in the bottom I have a cos x. All right. Secant x is the same as 1 over cos x, correct? And we're going to times it by 1 minus sine x over 1. And then we're dividing that whole numerator by cos x. When I divide by a cos x, what's that the same as? Multiplying by 1 over cos x. So I get 1 minus sine x over cos x, because if I multiply this numerator times numerator, denominator times denominator. And now I'm going to multiply by 1 over cos x. So I'm going to get 1 minus sine x over cos squared x. Now I can stop here and multiply by the conjugate over here. Or does anyone know what I could replace cos squared x with? Cos squared x? So what can I replace cos squared x with? 1 minus sine squared x, yes? So on the top I get 1 minus sine x. On the bottom I get 1 minus sine squared x. What is 1 minus sine squared x the same as? The difference of squares, what's it the same as? 1 minus sine x, 1 plus sine x. So this stays the same. And this turns to 1 minus sine x, 1 plus sine x. These cancel, and I'm left with 1 over 1 plus sine x. Ls equals Rs. So tomorrow we're finishing up proofs, and then you're going to have questions on proofs. But for tonight, that you get to work on the other homework if you haven't finished it yet. If you did finish it, you have time off.